Instead of using balls, let's use square weights so they don't roll around as much. Now here's our slat, and there's our weight. Let's shrink it down a little. Now let's put two of these weights at two distances from the center and two weights at the same distance from the other side. This will balance. Now we're going to say something you may not be familiar with. In fact, it would help a lot if you had a little toy model of our balance beam. But if you don't, just follow along. Now it turns out that if you were to move the two weights on the left equal distances, one to the left and one to the right, this would still balance. You'd be able to see that on the toy, or you could experiment with a teeter-totter in a playground. Now let's put the two weights at one distance from the center and move the two weights on the left equal distances. Now we know that this will balance. Not only that, but the one in the middle, that's right over the center point, wouldn't really tip the bar one way or the other. So we can just forget about it. Well, now we see that this balances. One weight on the left, at two distances from the center, and two weights on the right, at one distance from the center. They balance. Now, as mathematicians, we notice that we have 1 and 2 on the left, and 2 and 1 on the right. That's interesting. Now remember, we said that mathematics is partly guesswork. When we were counting, we noticed that 10 ones is 100, and we guessed that 10 hundredths was 1,000, and that worked out pretty well. Now in our present case, we have an opportunity to make another guess. Suppose we had one weight and three weights. Where should we put that one weight to balance the three weights? Do you have a guess?